In this video, I present MetaFormer is actually what you need for vision paper from CVPR 2022, which proposes a new insight and a new general architecture called MetaFormer, and then a specific architecture called PoolFormer that beats the Swin Transformer. And yeah, let's just see that. When we look at the transformer module architecture, we can see that it is made of two main modules, which are attention and channel MLP. Attention is responsible for mixing the information among tokens, and channel MLP is performing some operations on each token separately and kind of mixes the information among channels instead. And there have been some attempts to replace this attention module with other sort of modules. For example, in MLP-like models, they are trying to propose spatial MLP as an alternative to attention to mix the information among tokens. And channel MLP is the same as what it used to be, just to mix the information among channels. But in this paper, they're proposing a general architecture called MetaFormer. And in MetaFormer, they're saying that it doesn't matter what token mixer you use. And as long as you follow this architecture pattern, that there is some layer normalization and token mixer to mix the information among tokens, a residual connection, a layer normalization again, and a channel MLP, and then layer normalization again, when you have this MetaFormer architecture, you should have a very good performance. And that's a strong claim, isn't it? And it's kind of interesting because when I talked about a ConvNeXt for 2020's paper, they proposed a new module architecture called ConvNeXt. And in ConvNeXt, it's kind of similar to what we are seeing here as MetaFormer, because instead of token mixer, we are having these 7x7 convolutions. We do not have any skip connections, so it doesn't fully follow the MetaFormer architecture. But that 7x7, since it is a depthwise convolution, it doesn't mix any information among channels, and it only pays attention to mix the information among tokens. And then following by that, we have a layer normalization and a channel MLP, the same thing that we have in MetaFormer. So that's kind of interesting. But in this paper, to practically prove that this MetaFormer usually should work, they are replacing an embarrassingly simple module, as they say, for this token mixer, which is pooling. And when I say pooling, I mean the same average pooling that we are using it when we are having a CNN architecture, that it doesn't have any learnable parameter, and it also doesn't have the quadratic complexity in memory, the issue that the attention has. But yeah, when we look at the code that they provided in the paper, we are seeing this. In the forward function, when we receive x, the x shape is b as the batch size, c as the dimension of each token, and the number of tokens are h times w. And you might wonder, why do we have h and w? Because originally we have a sequence of tokens, right? So it's not a problem because we can simply reshape it to have a grid of tokens with some height h and some width w. And then we can do 2D average pooling, the same thing that we can perform on images. And the good thing about it is that it does the operation on each channel separately. So it doesn't mix the information among channels and only among tokens. So we can consider it as a token mixer. And what is self.pool? Self.pool is nn.average pooling 2D, which has a pool size of 3 always, a stride of 1, and a padding of pool size divided by 2. And pool size divided by 2 ensures us to have the same number of tokens as before. And yeah, that's it. And one strange thing that we can see here is that after doing the pooling, they have a subtract, which they say self pool of x minus x. And this minus x is because in the original MetaFormer architecture, we have a skip connection, and they want to neutralize this skip connection for some reason. but they didn't provide any actual reason in the paper, to be honest. And I really don't understand. Maybe they did a couple experiments and they realized that by doing the subtraction, we can get a better performance. Who knows? But yeah, that's what they proposed. And even though it is embarrassingly simple, when we look at this figure, which the x-axis is max, and if you don't know max, it stands for multiplication and accumulation operations, which is, as the name suggests, the number of multiplication and additions that we do. And the y-axis is ImageNet top 1 accuracy. And surprisingly, by doing fewer multiplication and addition, PoolFormer can have a better performance compared to vision transformer counterparts like DIT or MLP-like models like ResMLP, or even RSP ResNet, which is ResNet Strikes Back ResNet. It's also a very interesting paper that they just try to change the training procedure of ResNet, if I understand correctly, and surprisingly, they're getting a much better performance. And now let's just see the model architecture. So given an RGB image with a height of h and width of w, our model is made of 4 different stages. And as we go deeper in this neural network architecture, we end up having a smaller spatial size and having more channels, the same design principle that we follow when we design a convolution neural network. And so first, when we have an image, we pass it through a patch embedding, which does 4 times downsampling. And for this downsampling, they are using a convolution with 7x7 kernel size and a stride of 4. Then we have a couple of PoolFormer blocks, and then we have the patch embedding again. But from here on out, these patch embeddings, they are doing 2 times downsampling. And for doing that, they are using a convolution of 3x3 kernel and a stride of 2. And yeah, that's the main idea. And they propose different variants of small and medium with different numbers. And these numbers are, for example, let's just pick the 12, the first one. Then by simply replacing the L with 12, we can see the number of PoolFormer blocks in each stage. So by replacing 12, we have 2 PoolFormer blocks at the stage 1, 2 PoolFormer blocks at the stage 2, 6 PoolFormer blocks at the stage 3, and then again 2 PoolFormer blocks at the stage 4. So this is what these numbers mean, and the difference between this small and medium is the number of channels. So for small, we start by having 64 as our initial channel number, and then we double it to 128. But for some reason, instead of using 256, they are using 320, and then again, they're using 512. But for the medium, they're starting by 96, and they always doubling it as we go deeper and deeper in this neural network architecture. And by looking at the result, we can see how good the PoolFormer is. But I guess they are making a mistake here, and this Swin mixer that they are denoting here is actually the Swin Transformer if you look at reference 35, which is actually a vision transformer, and vision transformers are using attention. But for some reason, I guess they are mixed that up and categorized that as a spatial MLP, which is wrong. But let's just forget that. And by simply comparing this, for example, the best Swin Transformer one, which is Swin Mixer B as the base, and D24, it is having like 61 million parameters. And by comparing that with PoolFormer Medium 36, we can see that PoolFormer Medium 36 has 56 million parameters, so fewer learnable parameters. And comparing the max, Swin Transformer has 10.4, but PoolFormer now has 9. So with fewer parameters and computation, PoolFormer actually achieves 82.1, which is more than what Swin Transformer achieves, which is 81.3, which is impressive, isn't it? And by just looking at this figure, we can see the trend. This figure actually just depicts the same table, but it is now more understandable. So the figure at the left, it compares the multiplication accumulation operations, and the figure at the right compares the model size, which is the number of parameters. And in both cases, PoolFormer wins and is having a better ImageNet top 1 accuracy, while it has fewer parameters and fewer multiplication and accumulation operations. And finally, we can also use PoolFormer as a backbone of object detection, which is the table at the top, and also backbone of semantic segmentation, which is figure at the bottom. And in these cases, if we just compare PoolFormer backbone versus the ResNet backbones, or PVT, which is Pyramid Vision Transformer, we can see that our PoolFormer actually, even in these cases, it achieves a better performance on object detection and semantic segmentation. And that's all I wanted to present for MetaFormer paper. If you enjoyed it, don't forget to like and subscribe, and until the next video, goodbye.